the future of modelling might look like, depending on the types of data that we get from Ken and the types of questions we want to answer, which will be what Shweta's talking about next. So I'm going to talk firstly about the need for multiple different types of models and going beyond simulations. I probably don't need to spend too long on that given the audience. We know simulations are great, but we probably need a bit more. I'll talk a bit about approximation models and successes and failures, and then I'll look to the future and see what sort of things we could possibly do. So I have to start by saying I like simulation models. I think they're great. And basically, if we knew what the network was, if we were living in the 1984 world of Eames et al., and we could measure everything and know everyone's contact network, we could probably do an awful lot with them. And so it's theoretically trivial, although probably quite computationally demanding, to run lots and lots of simulations. And in some ways, if we're dealing with a really major public health issue and we really want to put all the details in, I would always go to a simulation at some level. So we've got things like Neil Ferguson's work on pandemic flu spreading through Southeast Asia, which, although it's spatial, is to a large extent based on networks. We've got Ira Longini's fantastic work, which again is based on networks and interactions between individuals. And again, this is for pandemic flu. And just to show that I also do it, this is work on cattle networks, looking at the dynamic pattern of movements of cows through all the farms in the UK. And what's nice about this is the government actually collects the network data for us. So we do have a good idea of what it is, and we don't have to put the time and effort in to try and collect the information. But so having said that simulations are wonderful and that's what we'd use in an outbreak if we knew all the information, what's the problem? Well, the problem is, in most cases, we don't really know what this underlying network is. It's what Ken said, you know, we're scrabbling around in the dark and we know little bits and we're trying to piece it all together. So the networks we've got are usually approximations, and also they generally tell us about the past. So all the studies that have been done, you know, it tells us about what the network was like 5 years ago. It doesn't tell us about what the future network is. So we need really something that will produce future networks. How can we predict those? We need ways of being able to capture all the uncertainties that are in the network. You know, do you always meet this person on a Tuesday, or was it just a random chance event? How do we put those uncertainties in? And then we need also some intuitive way of understanding what all this network complexity does. And what we'd really like is we'd like the sort of the standard tools, you know, bifurcation diagrams, stability analysis, everything else that we've developed over the last sort of 100 years or so with sort of standard ODE models and extensions. But we'd like to be able to apply that to all of the interesting and complexities that we get out from networks. So what I think we need is some form of approximation model. And I've heard sort of several people, Frank Ball touched on it, Lorenzo Pellis touched on it. What we need is some sort of approximation model to bridge this gap between the standard ODEs that we all understand and the network structure that we sort of don't. And there's been sort of 4 main different approaches in this. The one is the sort of branching theory and susceptibility sets that go back to Odo Dietman and Frank Ball, which were ways of looking at local network structure and trying to think about what the long-term dynamics are and the early stage dynamics. There's some very nice work on probability generating function models by Eric Volz, which again look at our sort of connections to the world and the variability in those connection sizes, our degree within the network. There's some interesting work by Kieran Sharkey, which I still don't understand, and I've never really spoken to anyone else who seems to understand it, which is it's some sort of pairwise model, but it works on all the edges within the network. So it's a very large and very complicated system, but it seems to give an incredibly good handle on what's going on within the network. And then finally, and not surprisingly, this is what I'm going to talk about most, is these pairwise models that started off with David Rand, who was here at the meeting 20 years ago, and then have been done by myself, Ken Eames, Thomas House, and Isvan Kiss, who've successfully gone sort of more and more theoretical probably with it and developed more and more interesting insights. What we found recently is that all of these produce effectively equivalent results if we're looking at the simple SIR model on an unclustered, ever-branching tree of a network. And in fact, we believe, and some people will say they know, that these results are absolutely exact. So I'm going to take you through this very, very quickly because it'll either be sort of bread and butter and people will understand it all and know it already, or you just won't care. So we start off with a sort of standard SIR model for how infection spreads, and what we're interested in is just a little pointer, is the sort of beta S item, the interaction between susceptibles and infecteds, which is the only sort of non-linear and interesting term in the dynamics. Oh, yes, it lines them for me. And that transmission, in a network sense, is only going to happen when we've got a susceptible pair next to a susceptible infected pair, a susceptible connected to an infected individual. And so if we relabel these terms, what was beta SI, we just say, well, it's a susceptible infected pair, it's these two individuals connected together in the network. We get a new set of equations, and actually, these equations are exact. If I could solve these equations, it would tell me everything about the dynamics on a network. The problem is, from these equations, I don't know what the number of susceptible infected pairs are in the network, and so I've got two choices left. I either approximate it, I either guess what it might be, and generally what you could do is you could say, well, it's the probability a susceptible is next to an infected, and we choose them both at random. That takes us back to our standard SIR type model. Or I do the more complicated thing, which is write down an equation for the number of these pairs. And that's this sort of moment generating approach that we've taken so far, of thinking of these higher order units within the system. So just to very quickly take you through this, if I'm interested in an SI pair, which is the main thing that wants to go into the equation for the singles, the S's and the I's within the system, then I've got two processes, or several processes that go on. I can make an SI pair because I've got an SS pair, which is the one I'm interested in, and that S gets infected from outside the pair. In which case, I end up having this SSI triple term in here, and not surprisingly, these triples are going to be the things that cause the problem. The other things that can happen are things that happen within the pair, which are quite nice and easy. So my infected individual can recover in any way, shape or form that we want. I can actually have infection within that pair. So my I infects the susceptible that was there, and therefore I've got infection going on. Or my susceptible individual can be infected from outside the pair, and again, this is written down as a triple that I need to have an I next to that S who's already next to that I. And maybe I'm not standing in the right place. And the problem is, not surprisingly, we've got these triples. What do we do? Well, we can either write down an equation for triples. Thomas has done this with a PhD student, and it just gets horrible and messy and ugly, and you need a PhD student with real maths brains and enthusiasm to actually take it on. What most of us have done up until now, which is nice and easy, is we approximate the triples in terms of pairs, and so we say an SIR, for example, triple is an SI triple next to an an SI pair next to an IR pair, given the fact we've counted this I sort of twice because it's in the middle. And so we end up with a relatively simple formula that approximates the number of SIR triples or any other sort of triple that we could think of. And I'll just say briefly that this n-1 over n term at the beginning is to do with the degree of these individuals. So n is your degree, your number of contacts, and there's an n-1 in front of it all, because if one of your contacts is already a susceptible, that decreases the number that you've got freely to choose that could be a recovered individual. So I don't want to say anything more about the sort of dynamics of all this and sort of how you go about constructing these equations, other than it enables us to close the equations and simulate a full epidemic. So with a set of about 6 equations, we can put some form of network or spatial structure into the dynamics. And it's been shown, under certain caveats, that this is exact for an SIR model on a regular unclustered network. So if we've got an ever-branching tree of connections, this approximation that we put in here actually works, which is good. And just to show that it does work, here's a nice... just to show you it does work, here's a simulation. So this was done relatively quickly when I realised I'd got to write this talk. It's 10,000 individuals and exactly 4 contacts per individual on a random graph. We get all these blue dots from the simulations, and the red is the pairwise curve. And as you go to bigger and bigger networks, the simulations collapse closer and closer to that red line. So we're convinced that for something as simple as this, it tells us something about structure. There's only a limited number of individuals that we interact with, and we interact with them strongly. It tells us about the structure that's there and how it affects the sort of infection dynamics. So again, I'm sort of back to what's the problem. You know, we've got a model that seems to work. So what more do we need to do? Well, these approximation models obviously aren't going to be perfect. They're an approximation, but there's sort of a few sort of areas where we know they work incredibly badly, where we need to think in more detail about what to do next. And really, the rest of my talk is going to be about these questions, and I don't really have any answers to any of them. And the 4 things are going to be sort of SIS dynamics. So rather than SIR, what about things for sort of sexually transmitted infection? Clustering, and by which I'm generally going to talk about sort of triangles within the network, triangular connections, but also sort of longer loops, 3 loops, 4 loops, anything you want. What do we do about all this different heterogeneity that Ken talked about? All these individuals are different. How do we actually pack all that into a useful and usable set of equations? And then finally, dynamic networks. And I think everyone keeps talking about dynamic networks. We know they're not static. What can we actually do? So SIS models, they're the basic thing that you'd want to use for most sexually transmitted infections. And sexually transmitted infections should be the ideal place where we're using these network models. It's relatively easy, although it invades people's privacy, when you want to go and talk to them about their network of sexual contact. Hopefully, if I ask the audience, you could probably all remember who you've had sex with in the last month. You probably wouldn't know who you've spoken to that you could... Don't look so frowny, Andy. Are you frowning at that, or are you frowning at something completely different? If I asked you who you'd met, if I asked you who you'd met in the last month, you probably wouldn't be able to remember. So it's sorry. It was just I looked round and you were going. The problem that we have is the SIS model doesn't work well in this pairwise formulation. It fundamentally breaks down. So here's exactly the same plot that I showed before. I'm using 3 contacts just because I've tweaked the numbers slightly to make it look even worse. But we find that the approximation and the simulations really, really don't agree. So we need something else to try and take this forward. Just to give you a hint at what we've been trying, although this isn't necessarily correct, we've been looking at a few different types of ways of trying to capture the dynamics, and these plots are showing changes in the pairwise transmission rate, the risk of transmitting across a contact, with different sorts of models. And we do sort of a full simulation in black. We've got ODE models. We've got the standard pairwise model. We've got a new pairwise model which is in cyan, which counts the number of times someone's become infected, which seems to be quite a good way of working out their position within the network, and also capturing some of the local structure that develops that you lose when you allow the person normally just to recover back to susceptible. And then we've also got what's known as, I call them star models or neighbourhood models, where instead of just looking at pairs, you look at the entire neighbourhood around an individual and say, how well does that sort of Can you calculate how many susceptibles and how many infected you have in your neighbourhood? And being as this has a neighbourhood of 3, that's actually quite an easy thing, and I can write down the code to do it. I don't need to get someone more clever to look at it. What we find, which is quite interesting, is that if we want to try and understand the prevalence, then actually these star models that take the entire neighbourhood into consideration tend to do incredibly well. So what I'm showing here, and this is probably the best one to look at, is the difference between the quantity we're looking at, in this case prevalence, in the simulation models compared to these approximation models. And what we find is the pink line, which is these star models, these neighbourhood models, do incredibly well at capturing the prevalence. They don't do as well if we're trying to understand the growth rate in the system. And if we really want to know about the growth rate, it seems that it's much better if we just count the number of times that an individual has actually been infected. But clearly, and all my sort of things for the future are probably going to appear in red if I've written this talk correctly, there's a need for these more theoretical developments. But I think this has got huge impact. We really don't understand how to do SIS models, and yet they should be the thing that we're working on for networks. So the other thing that I've sort of said we try to do is clustering. Several people have mentioned clustering in a network context here. These triangles within a system of contacts, so I know Ken, and Ken's talked to Shweta about the talk, and Shweta's talked to me, so we've formed this social triangle already. We've done some early work on trying to understand what the impact is of adding clustering, and the problem in some ways is, what does it mean to add clustering into a network? Well, you can obviously form a triangle and do something with it, but what do you hold constant? So here we've looked at holding various things constant, so that the top line holds the transmission rate constant across a pair. What happens if you sort of have basically an identical biology and change the network? What if you change the network, but what you've really done is you've gone out and done a field study and you've measured the early growth rate. So your network's changed, but actually you want to keep the early growth rate constant. What does that do to things? And then the bottom line is, what if you could measure R0 and keep that constant? And what we find is that for various things, so this is the final, so down here is the final number of susceptibles, which basically tells us about how big the epidemic's going to be. This one tells us about the maximum, the peak prevalence. So this is an SIR epidemic, up and down. What's the number at the peak? And then how long does it get to the peak? And what we find is that all the patterns of things change as we go from no clustering up to relatively high clustering, depending on what we hold constant. So it's actually quite a difficult question to say, what does clustering do? Well, the question is what are you holding constant? Is it the fundamental biology and you're changing the network, or is it that you've observed something and you're matching to that observation, but you just don't know various things about the network structure? But I think if we want to get to clustering, and this looks probably more complicated than it is, and this is a slide I've grabbed from Thomas, we probably want to start thinking about clustering by looking at the simplest examples we can. And the simplest example of a clustered network I know is a triangle. And this is just a triangle sitting there on its own with no connections. And we've been trying to study this problem in quite extreme detail. And this is a map of how you move through the space of triangles from starting off with sort of just one individual infected and 2 others susceptible, down to sort of having everyone recovered from it. There's this huge path of transitions. And what we find in this is actually it's the random recovery of individuals that tends to break all these approximation models. So if individuals are infected for a fixed amount of time, we effectively go to like a percolation process, and we can do everything with these approximation models. We've got some very good understandings. But if we've got random recovery, so you're infectious for an exponentially distributed period of time, then that tends to be the thing that breaks the approximation models. Maximum entropy, which is an idea that's been put forward for trying to sort of formalize these approximations in clustered systems, appears to offer the smallest errors. But again, there's lots of complexity. Sometimes the standard pairwise model works better. Sometimes it's maximum entropy, sometimes it's that. So it's not an obvious story. And I think, again, more work needs to be done theoretically to look at this. The other thing to realise is, the household models that Frank talked about are a nice way of thinking about a clustered model. I mean, each household has this highly clustered structure, and yet we've got some very, very good analytic attraction. So are there ways that we can build in the understanding that we get from these sort of models into the clustered models that we need for networks? So in general, I think there's a huge avenue for sort of theoretically motivated people to create the next generation of these approximation models that really take into account how we should put clustering in a network system. So my last sort of two examples are sort of extreme heterogeneities is the first one of these. This is taken from this contact survey that Ken talked about that we did. And fortunately, we've got some sort of very interesting people filling in the network. So we've got school children, we've got an air hostess, we've got a fireman, and we've got a granny. And what you see here is their set of links out from their sort of central node, which is this triangle. And I can't quite remember what all the different things are, but the size of the length of the link is how far away from home they are. The size of the node is how strong the connection is, and then these squares are sort of groups of individuals they met. So not surprisingly, the air hostess met about 342 people on the plane. She knows this because it's that, and the fireman probably met these 20 people at work who are in the fire station with them. And we've got all these complicated cross connections going on. So what we see is that this is an incredibly heterogeneous system. There's an awful lot of variability. We can make this sort of more explicit, and we can say one of the problems is the huge degree in huge differences in number of contacts. These are our results again, and what we find is there's some sort of power law slope to the results, that there are people out there with incredibly high numbers of contacts, and there are people with very, very few. And how do we put that in? Well, we can put it into the pairwise model. We can count susceptibles with N contacts and infecteds with M. What this does is it suddenly inflates the number of terms that we've got. It's not obvious how we deal with that sort of computationally, if anything. Kieran Sharkey's method brings this in automatically, but again, you have to track all the individuals within the network. And then Eric Volz's model automatically incorporates this, but it's got some assumptions about it being a random configuration model with random contacts. So it's not obvious how you try and bring in correlations and other sorts of structure in there. A bigger problem than just this degree, the fact that we've got heterogeneity in degree, is the heterogeneity in all the other sort of structures that are in there. And Ken spoke sort of quite well about it. Some links are sort of strung, long, frequent, sort of those that we have with family, whereas others are weak and rare. The person you sort of bought coffee off, you're probably not going to see them again, and you're probably not going to spread much infection to them. Some contacts, like these over here, are interconnected and clustered, where others are not. And then there's also sort of correlations that are in there between the demographics of all these individuals. Most of these school children are all going to be of a similar age. They're going to mix within class quite strongly. You'll probably find most of them mixing, as this granny was sort of with older people as well. So how do you sort of feed all that in? In principle, we can do it. We just need to inflate our number of compartments within any sort of model. But it very, very quickly number of classes is going to grow exponentially. We're just going to be bogged down with the amount of system we've got. And really what we want to do is we'd like to develop models where this network structure almost arises automatically. If we could work out how these networks sort of generate themselves, or we could feed that into a model, then we'd actually have a mechanism that allowed us to put the network structure in without having to specify it with millions of different parameters. So I think that's almost the sort of the next step that we need for these extremely heterogeneous systems, is can we develop simple underlying models that will almost generate the networks for us that we can then build into the transmission processes. And then the final thing, and again this was something that Ken spoke about, we should have spoken beforehand and sorted out these overlaps in our talk, but there we go, is that the networks are dynamic at a huge range of scales. So our social patterns change during the day. So this was the day that I sat down and wrote this talk, and not surprisingly, I met my wife and kid first thing in the morning, and then I met people at work, and then I met a slightly different set of people at work in the afternoon, and then I went home again. So there's a dynamic change throughout the day. This probably isn't going to be important for most of the infections we're thinking about, because the infection dynamics aren't going to change over this time scale. However, at slightly longer time scales, we notice that there's changes. So this is the change in the number of contacts over a week, or total contact time. And what we see is there's a distinct drop for most people on a Saturday and Sunday, although that drop starts happening on a Friday. It almost looks as if most people sort of have most of their contacts on Wednesday, Thursday, and most of these actually tend to be work contacts, and there seems to be a sort of go home early on a Friday effect and a hangover onto a Monday effect. So there's a pattern, there's an underlying pattern of change over a week, but sort of within that there's a change in who you've actually met on each day. At a longer time scale still, there's these age-dependent effects. I'm not quite sure whether it's down. I was debating whether it's downhill from 50 or actually downhill from in your teens. And I think it's actually downhill from your teens, and this blip here is just because you meet your children's friends. So really, there is this gradual decline in your pattern of contacts. But it's not just the pattern, it's also who you meet. The people I met back when I was a teenager and into my 20s are a very different subset to the people I know now. There's a few overlaps, but not that many. So, our contact patterns changing all the time. And then finally, and it's sort of been referred to quite a lot, is there's also this change due to a consequence of infection. And the nice work of Pedro Hani, when he was looking at at whooping cough and measles and how they interact, is really because of the change in the network structure that you isolate yourself when you're ill. This is an example from the cattle network. And what we can actually see is that the infections that move through the cattle network have brought in regulations, which in turn have changed the cattle network itself. So again, you get a system here where the network allows the infection to spread, but because of the infection, there's changes to the network. What we actually find with the cattle network, which is quite interesting, is that the farmers actually very quickly work out a way around all these regulatory changes, and the networks go back to trying to move cattle as freely as possible, which also moves the infection as freely as possible. So I think that the problem with dynamic networks is we need a new modelling approach, firstly, to be able to get it in. We need the data that Ken hopefully is going to generate over time and when people are ill to try and actually sort of reinforce that. But we almost need a new vocabulary. We're not very good at talking about dynamic networks. We haven't got the tools, we haven't got the nomenclature to actually deal with it. So finally, and I think this almost goes back to what was said about sort of what these meetings are sort of for, to bring these people together. We'd like to be able to bring in sort of theoretical insights from these very simple exact models that we can study. We'd need richer data sets on the networks to be able to sort of test our ideas of how infection spreads. And then we probably also need to bring in these large-scale simulation results where you can actually study things in detail to try and understand the things. But hopefully, I think there's certainly enough questions to keep us going for the next 20 years, if not longer. Thank you very much.
Well, as a granny, I feel I need to go and find a shawl and some knitting on. A few quick questions to Matt, remembering that we'll have an opportunity to talk to all three speakers at the end. Yeah, Andrea.
Well, very nice talk, and I was wondering, you mentioned that the problem with the clustering comes often from the exponential infection time. It seemed to me that the same might be true for the SIS model. So I was wondering, since we know that the exponential is not a good assumption, would one think of fair approximation for non-Markovian infection times?
You can do that. I'm looking for Lorenzo, who's been thinking about it. Lorenzo, who will know far more about it than me. It can be done. It's not trivial, and it becomes quite complicated because you have to think about the time that someone's been infected, and then you've got 2 of those within the pair, which is just messy. We believe it can be done. What's interesting is it doesn't seem to solve the SIS problem. So I've looked at the SIS model with, so you can show that actually it doesn't change the endemic level of infection if you actually put in a constant infectious time. So it solves some issues, but not all of them. But it's an interesting way forward, and it's something we are thinking about.
I was planning to ask the same question as Andrea. But
Okay.
in the same spirit, perhaps for SIS dynamics, I suspect that the Markov property is kind of essential. So if you leave that, then theoretical work will be very hard. It's also a reply I got from Liggett when Tom Liggett about this questions like what can we do if we don't assume Markov model, and his reply was short, I don't know of anything. But it might be worth looking more into the fixed infectious period, so because that's an extreme case, as is shown by already Karikul Lasma, 82. You have worst case there, so, and perhaps the fixed infectious period you can do some things which makes it Markov.
Yeah, you can do some things with the fixed infectious period. Certainly for the SIR model, it works really, really nicely. I think the SIS model almost breaks down because you've got this exponential waiting time for how long it is until you reacquire infection again. And you almost can't get around that because it's part of the transmission dynamics. And I think that's the bit that tends to break it.
On that vein, if you go back to Otto Diekman's talk, where he sort of questions whether that exponential distribution is really the true thing, knowing that the model is wrong there, how much do we need to care about the detail of the network? I mean, clearly things are, we don't know everything, and how far should we go in trying to resolve the details of the network, and is that going to solve our problems, or is it perhaps at a different level that we need to concentrate?
I think we need a mixture. I mean, I'm going to say networks are important. I mean, it's what I do. But I think we need all of it in a way. We still don't really understand the dynamics of transmission. I mean, what is it that, and how much infection passes across, and what is it that triggers it? And it's not an easy question. But I also think the network structure is quite important because it does slow things down an awful lot. It induces a lot of local competition. It probably has impact on things like evolution. So I think we need it in to some extent. Whether the simple unclustered models actually tell us that much about what we need, and I think it's only when we start really putting strung clustering in, almost like sort of households and then larger structure around that we really start to see the true dynamics that we need.
I think we should go on to Shweta now, so maybe time for some questions at the end.